Hello and welcome to CSE 373, Section 4, Trees. Apologies for not having my face camera on for this video. I've been having technical difficulties with it all day, but hopefully the section video will still turn out alright. In today's section, we'll be going over some course announcements, reviewing AVL trees, and introducing a new data structure, tries. For course announcements, Exercise 3 is due on Monday the 24th with a late due date of Thursday the 27th. Additionally, Project 2 is due Wednesday the 26th with a late due date of Saturday the 29th. And finally, and probably the most important, the most important date is that we'll be having our midterm in class on Friday the 28th. So please don't skip lecture that day because we'll be taking our midterm in class. Additionally, if you need any accommodations, please reach out to us as soon as possible, probably today, just so we can take care of all of your needs before the midterm. Let's hop into some review. First, let's review binary search trees before diving into AVL trees. As a reminder, a binary search tree, or a BST, is just a binary tree that upholds the BST invariance. That states all the values in the node's left subtree must be less than our node's value, and all of the values in the node's right subtree must be greater than our node's value. If we looked at this example, we can confirm that the BST invariant is upheld for every node. For example, let's look at this 10 node. In order for this to be a BST, all the node values in the left subtree must be less than our 10 node, which we can see is the case, and all the node values in our node's right tree must be greater than our node's value, which is also the case. So that BST invariant is upheld for our 10 node. And what's really cool about BSTs is that every single node in our BST is also a BST. So if we wanted to actually verify a BST or a BST, we'd have to go through every single node and check that the BST invariant was upheld for every single node. And we can also see that this is the case. Take this 15 node, for example. As we can see, all of the node values in the left subtree are less than 15, which in this case is only 12. And all the node values in our right subtree, or 15 subtree, is greater than 15. So the BST invariant is upheld for a 15 node, and 15 is also a BST, as long as the BST invariant is upheld for every single node in our tree. Cool. However, there's a problem with BSTs. Like we talked about in class, BSTs can become unbalanced, which would result in many operations becoming slow, right? If we were to insert values in either an ascending or decreasing order, or ascending or decreasing values, then we would our BST would result in what we call the degenerate case, where our BST resembles a linked list. And this is awful because it means to insert a value or remove a value or look for a value, we'd have to look through every single value in our BST one node at a time, which would result in an O of n runtime, opposed to the quicker O of log n runtime, which we can guarantee if a tree is valid or balanced. But what does it mean for a tree to be balanced? Well, we know a node is balanced if the difference in height between subtrees is no greater than 1. And for a tree to be balanced, every single node in that tree would also have to be balanced. So we would have to compare heights of subtrees for every single node inside of our tree. Just as a reminder, the height of a null tree, which I'll represent null as a box with a slash through it, is equal to -1 for our purposes, and the height of a single node, which I'll represent just as a circle, is equal to 0. Think about height as the longest, the greatest number of edges it takes to reach a leaf node. So if we wanted to find the height of this 10 node, we would count the longest path from 10 to a leaf node, which in this case is 2 edges. So the height of this 10 node is 2. Great. Let's run through some examples of balanced and unbalanced nodes. Suppose we wanted to check if this 8 node is balanced. Well, all we would have to do is compare the heights of this 8 nodes left and right subtree. Well, the 8 nodes left subtree is a single node, so we know the height of the left subtree is 0. The 8's right subtree also consists of a single 9 node, so the height of 8's subtree is also 0. Since the difference in heights between these subtrees is 0, which is no greater than 1, we know that this 8 node is balanced. How about this 10 node? Is this 10 node balanced? Well, its left subtree is null, so its left subtree will have a height of -1, and its right subtree has a height of 1. Since starting at the root of our right subtree, there's the longest path to reach a leaf node is 1 edge. Therefore, the height of this right subtree is 1. Okay, 1 minus -1 will result in a difference of 2, and a height difference of 2 between the left and right subtrees, so we know that this 10 node is not balanced. Finally, let's look at these remaining 2 examples. For this to verify if this 8 node is balanced, we'd have to compare the left and right subtrees. Its left subtree has a height of 0. Its right subtree has a height of -1 since it's only null. The difference between -1 and 0 is 1 or -1 depending on which order you do it. So we know that this subtree is balanced. Finally, a tree consisting of a single 7 node. Its left and right subtrees both have a height of -1 since they're null. Therefore, this tree is balanced. Great. I don't know why I threw a 0. Let's do a check there, just in case. And a nice property of balanced trees means that a balanced tree with n items has a height bounded by log n, or its height is O of log n, which means we can guarantee O of log n operation runtime, which is really nice. If we wanted to run through some examples, we have a balanced tree for this 8 node, like we saw in the previous example, right? How many levels are there in a tree, i.e. how long will it take to search for a particular item? Well, it will only be 1. There are 2 levels in our tree, maybe level 0 and 1, so we're only 1 path away from reaching the farthest node from our roots. And this is how we can kind of uphold the log n property. And one very nice property of a balanced tree is that a balanced tree with n items will have a height of O of log n, or its height will be bounded by log n. And this is really cool. This is how we can guarantee O of log n worst case runtimes for our binary search tree or tree operations. Right? If you think about it, the amount of time it'll take to look for a particular item or insert an item or remove an item will be the time it takes to traverse the longest path in our tree. And if we can guarantee that the longest path in our tree, or the height of the tree, is O of log n, then we can guarantee these O of log n runtimes, since we'd only have to, at worst case, traverse log n edges. Really cool. So we would just need to make sure our tree is balanced in order to guarantee these log n runtimes for our tree operations. How do we do this? AVL trees. As a reminder, AVL trees are special BSTs that remain balanced no matter what. And they do so by rebalancing themselves using rotations anytime an item gets inserted and the tree then becomes unbalanced. And subsequently, they'd also use rotations if an item were to get deleted and the tree were also to become unbalanced. And there are 4 cases to consider. Rotations aren't a huge focus of this section, so I won't spend too much time on it, but be sure to, I think it'd be valuable to review how to perform these rotations. And luckily enough, we have this AVL rotation walkthrough presentation that you can definitely check out. It's linked on this slide, so if you were to go to the course website, access this slide and then click on this link, it'll take you to a pretty nifty presentation on AVL rotations. All right, so now pull up the section 4 worksheet and attempt question 1A through C on the BST/AVL portion of the worksheet. Pause the video and then unpause when you're ready to discuss. All right, so this problem asked you to validate whether or not a tree was a BST and an AVL tree for a series of 3 trees. So the first question asked is if this tree is a valid BST, and as we can see that this tree is not a valid BST because this value 2 is in the 7's right subtree, which contradicts our BST invariance. So it's not. And then we are asked if this is a valid AVL tree. And remember, an AVL tree must be a BST. So this is not a valid AVL tree either. Is this a valid BST? Yes. Every single node in this tree upholds the BST invariance. Is it a valid AVL tree though? No, because we see that the 7 node is unbalanced. Its left subtree has a height of 0, while its right subtree has a height of 2. Oh, and additionally, our 42 node is also imbalanced. So a lot of imbalances going on here, where its left subtree has a height of 1, and its right subtree has a height of -1. Okay, for 1C, is this tree a valid BST? And yes, it is. All the nodes uphold our BST property. Is it a valid AVL tree? Looking at this tree, I can't spot any imbalances, so it is an AVL tree. Great. Now pause the video and attempt problems 5A through C. Moving forward, problem 1 asks you to write down a type big O for inserting and finding an element in a BST. Well, like we talked about, the worst case runtime is O of n for both because of this degenerate case that non-AVL BST trees can run into, or the linked list like tree. Okay, what's the type big O runtime for inserting and finding in an AVL tree? Like we also talked about, these operations are guaranteed to be O of log n as long as our tree is balanced, because the number of levels the number of levels in our tree will grow logarithmically if we can guarantee our tree is balanced, which is really nice. Finally, what's the runtime for finding the minimum value in an AVL tree containing n elements? Well, like we talked about, the runtime for finding an element will be at worst the longest path in our tree. And like we said, the longest path in a balanced tree will be O of log n. Therefore, finding the minimum element will also be O of log n. It's no different than finding any other element in our tree. Awesome. Now pause the video and attempt problem 6A through C. For this question, you were asked what are the constraints on the data types you can store in an AVL tree. And thinking back to when you were learning about tree maps and tree sets, all keys in an AVL tree and BST trees need to be comparable. We need some way to order the elements so that way we can check if the BST or AVL tree, if the BST invariant is upheld, and we were able to properly sort our elements in our tree. And since AVL trees maintain their keys in sorted order, we have to be able to compare keys to decide whether to go left or right at each node, etc. So we wouldn't be able to perform, let's say, binary search with our trees if we didn't have a way to compare keys. And there are no restrictions on our tree's value types. I'm just going to highlight that. Cool. For problem 6b, it asked us, when is using an AVL tree preferable over a hash table? And in theory, right, an AVL tree would have a better worst case runtime for operations, especially for Git, right? Because theoretically, the worst case runtime, or like, okay, the worst case runtime for a hash table's Git operation will be O (n). And that's if everything maps to the same bucket. But in practice, this will never happen if we can use if we are guaranteed to use a good hash function that will spread elements out. So the worst case in practice runtime of a hash table is O of 1, but in theory, the worst case runtime for an AVL tree is O of log n, which is quicker than the worst case runtime for a hash table Git. And finally, when is using a BST preferred over an AVL tree? One preference we can have is that AVL trees, since they're constantly rebalancing themselves, they're very complicated to implement. And so this means BSTs are way easier to implement and debug than trying to implement your own AVL tree. Another reason we could prefer a BST over an AVL tree is if we're guaranteed that the elements inserted into our BST won't cause our BST to be quote-unquote degenerate, or we know that the elements inserted will have our BST be a balanced tree, then we may prefer that BST over an AVL tree. It may actually be quicker to look up our elements in the BST because we're not constantly, or it may be quicker to insert, find, or remove elements in a balanced BST over an AVL tree because we're not constantly having to do rotations in our balanced BST. So that's one thing to look out for. The runtime for our balancing operations in an AVL tree is constant, but all those small constant operations eventually do add up. Just something to keep in mind. All right, let's dive into the next subject, or next major topic in this section, which is tries. So tries are just another tree-like data structure that we'll be learning about for the first time in this section. Tries are a very specialized data structure, but they're very efficient at what they do. And that is, we can use a trie when we're storing keys that could be broken up into a sequence of characters, right? What is a key that could be broken up into a sequence of characters? Well, if we look at the keys that we're inserting into our trie, which is this funky looking tree on the right, we can see that each letter in our word keys, or our word keys can be broken up into a sequence of letters. For example, in our trie, SAP is broken up into S, A, and P. So words are a perfect example where they can be broken up into a sequence of characters. Another type of key that could be potentially broken up into a sequence of characters are numbers, right? Every single number could be broken up into a series of digits, where each digit is between 0 and 9. So like D0, D1, etc., until it's the last digit in our number. And we insert or store our keys by creating paths of nodes, where each node contains a single character from our key. And then once we insert the last character in our key, we will mark that node as being inside of our trie, or purple in this case, to indicate that our trie does in fact contain this key. We'll do some more examples of trie insertion later on in a couple of slides. So tries, are pronounced like trie, even though they're spelled T-R-I-E, is a data structure that represents a dictionary or set ADT. We've been working a lot with dictionaries lately, but if you think about it, right, sets are also a type of dictionary where every single element is marked as either being in our set or not being in our set. And in order for a trie to implement one of these ADTs, it needs to allow for the following functionalities, and that is adding an element, finding an element, and removing an element. So to add to a trie, like I said earlier, we essentially start with an empty overall root node. And then when inserting a key, in this case SAP, we would go character by character through our key and create a node for that character, and then create a path that will eventually represent our key. So we would start with the first character in our key S and create a node. We would then branch off of that S node and create a node for an A. Note, if there were already an SA node, we wouldn't have to create a new node, but in this case, since we're starting from an empty trie, we do have to create a new A node. And finally, we would go to our last character and insert that a P node into our trie. And additionally, since it was the last character in our word key, we would also mark this P node as being in our trie, or as the diagram shows, like purple. And this is how we would store the SAP key. And we can continue this process of breaking our keys down into nodes. And as it turns out, it will be really efficient whenever we can guarantee that our keys can be broken down like this and share common prefixes as well. Next, if we wanted to insert SAD, right, we would perform the same process of starting at the key's first character, which is S, then traversing down to the next character, which is A, and finally looking for a D node. Since our current trie does not contain a D node, we would create a new D node that's connected to the A node we were at previously and mark it as being in our trie. All right, suppose we wanted to add AWLS. It's the exact same process as we saw earlier. There's no A node connected to our overall root node, so we create that A node. And we perform the same process, creating a W node, an L node, and an S node, and marking it as being in our trie. One thing that I'd like to note is that our trie nodes must contain additional information. For example, potentially a Boolean as to whether or not they're in our trie, and they're allowed to contain other information, right? We can store values inside of these nodes. Just wanted to make some clarifications. Great. Moving forward, let's say we wanted to add A. Well, we would start at our overall roots and look for an A node. There is an A node, so all we would have to do is mark it as being in our trie. We wouldn't have to create any additional nodes. All right, moving on to searching in tries. If we wanted to search for particular trees, two cases either occur, and that's we find the key we're searching for and it's a hit, or we don't find the key we're looking for and our search results in a miss. If we wanted to search for Sam, we would just follow the sequence of keys, or follow the characters in the key that we're looking for. So in this case, this would be SAM, and since M is the last character in Sam, and it's marked as being in our trie, we return true. If we wanted to search for the key SA, we repeat the same process, starting at our overall root node, going to S, and then going to A. Since A isn't marked as being in our trie, we return false, and our search results in a miss. All right, if we wanted to look for A, we start at our overall root node and look for an A node. Our trie contains an A node, and since that's the last character in our key, we mark that as, we look to see if our A node is marked, and it is. So our search results in a hit. Finally, if we wanted to search for the key SAQ, SAQ, we would traverse our trie, SA, and then look for a Q node that's connected to this current A node that we're on. However, there is no Q node. So our search, quote unquote, falls off of the tree, and our search results in a miss. So there are two ways to miss, and that is if the final node that we land on isn't purple, or if we fall off the tree, and the next node in the key we're looking for is not contained within our trie. Cool. And finally is removing from a trie. There are two ways to remove from a trie. The first method is lazy deletion. So if we wanted to remove AWLS from our trie, we would traverse to the correct location, AWLS, and unmark this last character node as not being in our trie anymore. And that's all lazy deletion is unmarking a node if it's no longer in our trie. So this is the final state of our trie after using lazy deletion to remove AWLS from our trie. However, there's a slightly more complicated removal method that a trie can use, and that's normal deletion. We're not being lazy anymore. And what normal deletion is it upholds the invariance that all leaf nodes of our trie are marked as being in our trie. What does this mean? Well, let's suppose we call remove AWLS again, and we uncolor our S node. Since we want to uphold the invariance that all leaf nodes inside of our trie must be marked as being in our trie, we remove the unmarked S node completely, since it's an unmarked leaf node. Similarly, this leaves us with the tri-state on the one diagram over, and as we can see, there's still another unmarked leaf node, and that's this L node. So we remove it and continue moving up our trie. We also remove this W node, since it's an unmarked leaf node, until finally we hit this marked A node. This A node is marked and a leaf node, so we don't have to remove it. And that's how we're left with this final state, or this final trie, where all of the leaf nodes are marked. Cool. Oh, that's kind of ugly. But yeah, as we can see, all 4 of these leaf nodes are marked, so we don't have to remove any additional nodes. Cool. Pause the video here and attempt problem 1 for the trie portion of the worksheet. Cool. Moving forward, the first part of problem 1 asked you the question of, if we deleted all binary numbers of length 2, how many nodes would we have to delete in total using normal deletion? Well, the first part of answering this is identifying where all binary numbers of length 2 are stored in our trie. Well, we know a key is a binary number of length 2. If our trie, if there's a path consisting of 2 edges from the overall root to our current node, then we know for sure that node represents a binary number of length 2. And in that case, it turns out all the nodes in this level are binary numbers of length 2, since they all have a path of 2 coming from the overall root node. So if we were to delete these using normal deletion, we would unmark all of these currently marked nodes. Since these unmarked nodes are not leaf nodes in our trie, we will keep them in our trie, since they are connected to currently marked leaf nodes. So everything is good, and we won't have to and we will not remove any nodes from this trie. So the answer is 0, since we will still have pointers to the nodes for length 3 binary strings. And we will just unmark all of the nodes representing binary numbers of length 2. All right, part B for question 1 asks, if we deleted all binary numbers of length 3, how many nodes would we have to delete? Well, it's the same process. If we know all the nodes on this level are of length 2, and then all of the nodes on the next level represent all the binary numbers of length 3. So we want to unmark all of these. Once we unmark all of these, all of these nodes will now be unmarked leaf nodes. And since we're using normal deletion, we will remove all of these nodes from our trie. So we will remove all of these nodes. Once we remove all of these nodes, we will also have all of these unmarked leaf nodes representing all the binary numbers of length 2. Because these are unmarked leaf nodes, we will also remove these nodes. And then our final trie will only consist of these 3 marked nodes at the very top of our trie. So to answer the question, if we deleted all binary numbers of length 3, how many nodes would we have to delete? We would have to delete 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes in total. 12 nodes in total. Cool. Unmarking everything and then removing each subsequent level. So we're left with this final try. All right, next up is problem 2A through C, call me maybe. So pause the video right here and give this problem a go. All right, walking through the answers. Problem 2A asked you, suppose you wanted to transfer someone's phone book to a data structure so that you can call, a minor typo, all the phone numbers with a particular area code efficiently. What data structure would you use and how would you implement it? So it sounds like the client wants some sort of dictionary ADT. Dictionary where we can use area code to look up phone numbers, or it maps area code to phone numbers, or something like that, right? And we need to find a data structure to implement our dictionary. Two data structures that immediately come to mind are hash maps and tries. We can use a hash map where the keys are area codes and the values are a list of corresponding phone numbers. And then we would have to parse each phone number for its area code and identify all keys with that area code in order to look for all phone numbers that share a particular area code. The other way to implement this would be to use a trie, where we use phone numbers as our trie routes, right? Each node in our trie represents one digit of our phone number, and then we use our phone number digits to create our routes and to store our phone numbers in a trie. And then we would insert all phone numbers into our trie, and if you're looking for all phone numbers that shared a particular area code, we would then traverse down to that area code in our trie and then visit all of the children of the node corresponding to that particular area code. This is why tries are so efficient when storing values or keys, when storing keys that share a common prefix. We can traverse down to the end of that prefix and then just explore all of the children to efficiently look up all keys, or in our case, phone numbers, that share a common prefix, or in our case, area code. What is the time complexity of our solution? In both instances, it takes big theta of n to insert all of our phone numbers. Remember, this is in practice worst case time complexity. If we're doing like the theoretical worst case, it'd be O of n squared to insert all of our phone numbers for a hash table, or big theta of n squared. But this is our in practice time complexity because we're performing n constant time operations. For both as well, it takes big theta of e to look up all of our phone numbers with a particular area code, where e is the number of phone numbers with that area code, right? We're performing e constant time lookups. One thing I would like to note, however, is that the constants may be a little bit different during our constant time lookups. In order to insert a single phone number inside of our trie, the time it takes to insert a phone number is the time it takes to traverse down to where we have to insert the last digit of our phone number into our trie. What's the worst case traversal to insert a phone number in our trie? Well, that is creating or traversing a trie route or path containing the maximum number of digits inside of our phone number. We would have to traverse a path of that length to insert a new phone number into our trie. I'm going to let k be the length of our phone numbers. Then in that case, it would take kn time to insert all of the phone numbers into our trie. K in our case is still a constant, so it's still like a constant time insertion. But if we wanted to be very particular about the runtime of our trie, it'd take tries are O of k time to insert or look up or remove an element. Because the longest path in our trie will also be the longest, or the either the size of our keys or the maximum size of our keys when they can be broken up into a sequence of characters. So insert for a particular element is OK, but in this problem we're treating it as constant. Cool. What is the space complexity for our two solutions? For a hash map, our space complexity is O of n, where n is the number of phone numbers. And as well for tries, the space complexity is also O of n, where n is the number of phone numbers. In theory, though, tries will be more space efficient, as tries will store near duplicate phone numbers in less space than the hash map. Yeah, in theory. Moving on, now try to attempt this last problem, problem 3. Pause the video here, and then we can go over the solutions. All right, so this problem was quite similar to problem 2, where it asked us to implement a dictionary ADT that maps our numbers to all possible words that sequence of numbers can represent, given this number to letter mapping. And it looks like our keys will be sequences of numbers which we can break down into individual digit characters, and thus we can use a trie to implement this ADT or dictionary, where each node will be a digit, it will contain a digit of our key routes, and all values of nodes that correspond to keys that are actually in our trie will contain a list of words that are associated to that sequence of digits. Here's the solution. We can use a trie where the routes or branches are represented by the digits, and the node's values are a collection of words. In order to populate the trie, we would iterate through each word in the dictionary, convert the word into a corresponding sequence of numbers, and finally use that sequence as the key or routes to traverse the trie and add the word. And in this case, we can quickly look up all words that correspond to a sequence of numbers that are stored inside of our trie. Especially if they share a common prefix, we're now given the ability to efficiently perform this prefix type search, where, for example, we wanted to search for all words that corresponded to numbers starting with 1, 2, or 3. We could easily do that with a trie. And like we talked about, with tries, like let's suppose K is the longest length of a key in our trie, then all of our operations are O of K. Inserting an element will be O of K, looking up an element will be O of K, and removing an element will be O of K as well. Which is crazy, right? If K is a small constant, then effectively we also have a constant lookup time, which will blow our AVL tree out of the water. But once again, tries are very specialized, so they can't be used in every single case. What a cool data structure. That's everything from this section. And yeah, I hope you all have a great week.